So let's go with an example. Okay, let's say we discuss with customer and come up with a specification that both parties signed. Like we signed as a designer, hey, we are going to do this system, and the customer also signed that I agree that this specification captures all my intended usage, all my requirement. So this system says the XS3 code for a decimal digit. Okay, so we are dealing with single digit representation, the single digit values 0 to 9. So XS3 code for a decimal digit is the binary combination of the corresponding decimal digit plus 3. That means, let's say I have 5. 5 is represented as 101, right? Then XS3 code would be the binary pattern corresponds to 5 plus 3, which is 8. 8 is like 1000, right? So if my incoming bit pattern represent 5, let's say it is by 0101, then outgoing bit pattern or output from the circuit would be 1000. So we add 3 inside, and that becomes my output of the circuit. So implement a logic circuit which translate a 4-bit BCD, which is binary coded decimal, okay, which translate a BCD, 4-bit BCD. That means in the binary coded decimals, I can have values from 0 to 9. So if you remember, just to give you a hint, what is a BCD, you can search in the Google. BCD is that, let's say I have to represent a value, let's say 29. Okay, so instead of representing that 29 as a complete binary translation that we did in the number system study, instead of that, what we'll do, we will take each of this digit 2, 9, and each of this digit will expand into corresponding 4-bit representation. So 2 will be represented at 0, 0, 1, 0. 9 will be represented at 1, 0, 0, 1. So that's the BCD coding. Now it's saying that translate 4-bit BCD, that means it is dealing with one single digit, decimal digit. Okay. So we are incoming is a 4-bit BCD and outgoing is the converted XS3 code. So from this description, from our understanding, what we can do, we are trying to write down the corresponding input and output relations. So let's say I write down all my possible incoming 4-bit BCDs, which is from 0 to 9, right? It's decimal digit 0, 1, 2, 3, 4, etc. till 9. So let's say I have 4 input in my circuit, A, B, C, D, corresponding bit pattern represents my corresponding decimal value, right? So what is my output? So 4-bit BCD plus 3, that becomes a 4-bit output as well, right? So my input range is 0 to 9. That means I need 4 bits to represent 0 to 9. My output range is basically 3 to 12, right? Output of XS3 of a BCD is basically starting from 3. So 0 converted to 3, 9 converted to 12, and all the numbers in between. So range of the output XS3 is from 3 to 12. So that's why we also need 4-bit to represent that as well, those values. And how we write down the output functions? So here you see, instead of having a one single bit output, my output from this circuit is 4-bit output. So let's say those outputs are W, X, Y, Z starting from MSB to LSB, left hand side to right hand side. And we write down our needed output for corresponding input bit pattern. Input bit pattern 0, 0, 0, 0, that is value 0, XS code is 3, so that's why we have 0, 0, 1, 1. Take another example, 5, which is represented as 0, 1, 0, 1. Add 3 on top of that, it's 8. 8 is represented as 1, 0, 0, 0. That's in the output side. Let's say it is 7, which is like 0, 1, 1, 1. Then output becomes 10, right? 10 represented as 1, 0, 1, 0. All right. So this is the truth table. Then from this truth table, what shall we write? It's down the corresponding Boolean function. So we write it down in the SOP form. For the W, as we know how we write, we pick up those mean terms which has a corresponding one. So we pick up M5, M6, M7, M8, M9, that is sigma of M5, 6, 7, 8, 9 for the W. And if you notice, there are don't care term as well. Now let's explain this. For this problem domain, you see your expected input bit patterns are bounded from 0 to 9 because we are dealing with BCD digit, 4-bit BCD digit. That means at my input side, I don't expect any bit pattern correspond to 10, 11, 12, 13, 14 and 15, right? Just by the problem specification. Since problem says that, hey, make a circuit, just look at the problem specification again. Make a circuit, implement a logic circuit which translate a 4-bit BCD. So that statement actually bounding my input value ranges from 0 to 9. That means I don't expect value as incoming value of 10 to 15. So I don't need to deal with that in my circuit, and they become don't care. Now hopefully you now understand what is the origin of this don't care term in digital circuit design era, right? As I described in Boolean algebra 2 that time, that there is this very specific curious things that don't care comes into play and have major role in optimized circuit development in the digital logic world, which is not apparently very apparent in the math world. So math world deal with all the value combinations, no matter what. This is an abstract sense, but in a practical sense, from the circuit specification, we can identify that certain mean terms are not possible by the definition of the requirement. It's not possible to occur during the operation of this digital target digital circuit, and they become don't care. All right, so enough of that. So we write down SOP form with the don't care 10, 11, 12, 13, 14, 15, and we pick up for each of these output variable WXYZ, we write down its corresponding SOP form. So once we have this SOP form, we can apply our K-map technique. So we use our K-map technique, okay, and come up with these optimized expressions. So 1, 2, WX, Y, Z. And once I have it, then, so these WX, Y, Z are obtained from the K-map optimization, right? And from there, now what we are trying to do here, can we derive some common logic across this WXYZ, across this different output variable? Why? Because K-map focus is on one single Boolean function, which is either it is optimizing on W or optimizing on X or optimizing of Y. That means if there is a scope to reuse some of the intermediate logic that is being done for another output variable, it cannot predict, K-map technique cannot predict absolutely that I can go and reuse some of the functions that is already done in other output logic. So that's why we need to kind of little bit rearrange those logic, try to see if we can do something common across them. For example, here in the BC or BD, we can make it a B and C or D, right, by identity. Similarly, for the X, I can write down as B bar C or D, B, C, D whole bar. So look at this C or D, I can see there we can readily reuse them. So we do that, and we want to do the y equals cd or c bar d bar, and z equal to d bar. We cannot do anything else. So we can make a common term c or d. Then my w become a or bt, and x become b bar t or bt whole bar, which you can do an XOR circuit, or you can keep it like that depending on what type of gates you have available. All right. So once we have this, we draw its corresponding schematic. So basically what we do, we look at each of these functions. For example, w is a or b and c or d, right? So it is, we make a c or d, okay, from the combining c and d input through our OR gate. Take that and make it AND with b, right? And then output of that AND, which is b and c or d, or with a, and that becomes my w. Similarly, we place different logic gates into different to implement different output of that target circuit, and your circuit becomes like this. So what does it mean? It means that basically your schematic diagram, this one, and your Boolean expression, they are basically representing the same concept, right? Boolean expression of this different output variable are compact representation of what logic I need to operate between primary inputs, or this independent variable a, b, c, d. So that concept, that representation of concept can be done in a different way through a logic circuit schematic diagram. Logic circuit diagram, schematic diagram, they are all kind of interchangeable terminology there. But it, in a nutshell, it is basically representing your Boolean expression in a pictorial form, right? So your circuit diagram representing your Boolean expression in a pictorial form, and now from here, since we know each of these gate, we can make it through electronic circuit, as we have seen in our logic gate lecture, that each of these basic logics we can derive from certain logic circuits. We can make this and realize this on a piece of silicon, okay, on which we can make some AND gate, some inverter gate, some OR gate. How we make it, not our scope, not in our class scope, okay. But as long as we can make a Boolean expression logic with inverter and or not, even you don't need them, right? You can only express everything with a NAND expression, right? As soon as you can do that, you know that you can deploy certain electronic component which we can implement on a piece of silicon and make an electronic product out of this. So that's the concept I would like you to pick up, that we do the K-maps, we do the Boolean reduction just to make sure we can use minimum number of electronic component to make the target Boolean function. If we can use the minimum number of component, that means we are reducing the production cost of our target product, this electronic digital circuit product. That means we have a higher chance to success in the market. So there is a direct business need associated with this Boolean expression optimization and realization of the electronic circuit. So that's all for this lecture. If you have any question, please let me know in the class or send me email.